Bismillah ar-Rahman ar-Rahim. Welcome to this lecture. Today we will talk about discrete time systems. So our lecture is talking about discrete time systems. The function of a discrete time system is to process a given input sequence to generate an output sequence. Symbolically we will say that, okay, y of n is equal some transformation or process of x of n, where t is an operator which is transformation. So it's a transformation. Y of n is the output sequence. And x of n is the input sequence. We can also represent this as we have x of n with an arrow with t above the arrow. T means transformation, and the output here is y of n. So we can represent x of n going arrow in this direction to give us y of n. We can also use a box representation and say that we have x of n going to a system with t, whatever t is, and then you get y of n. So all those are different representations of a discrete time system. Notice that when we say discrete time system, we mean that the output is a sequence and the input is a sequence. So it's discrete time sequence input, discrete time sequence output. This is what represents a discrete time system. Okay? Okay. Let's go directly to the classifications of discrete time systems. Classifications of discrete time systems. Okay, and we'll take the first one to be linear or nonlinear system. So we'll talk about linearity. So linear systems, if given that y1 of n and y2 of n are responses to the input sequences x1 of n and x2 of n respectively, then for the input x of n equals to alpha x1 of n plus beta x2 of n. The response is y of n equals to alpha y1 of n plus beta y2 of n. Then we say that the system is linear. So we call the system linear if we have an input x1 of n that give us y1 of n, x2 give us y2 of n. We have a linear combination of those two as input, combination of those two input sequences as input to the system. Then we got exactly the same linear combination of the corresponding outputs. So this system will be linear. And actually this here is the superposition. Superposition applies. So we call that the superposition applies here. Okay. So the system, if this applies, we call it linear. If it doesn't, then we call it nonlinear system. Okay? So we call it nonlinear system. So let's take an example and see how can. Let's take a y of n equals to an x of n, b y2 of n equals to, just let's skip the subscript here, just put it in this way, y of n equals x squared of n, and c y of n is equal to a x of n plus b, where a and b are constants. A capital and b are constants. Okay. Solution. Okay, let's take part A and see. So we have three different systems here. We're going to check the validity of linearity for each of them by seeing that the superposition principle applies. So we're going to let here that x1 of n, we'll assume we have two inputs, x1 of n, it has transformation of y1 of n, which is equal to n x1 of n. And we have also x2 of n, which has the transformation here to be y2 of n, which is equal to n x2 of n. Now we're gonna assume that, or let x of n is a linear combination. Let's say a1 x1 of n plus a2 x2 of n. So let's apply x of n to the system and see that y of n is equal to n x of n. Now, what is x of n? X of n here is those two. So this is my x of n. I'm going to substitute this x of n here. So this one is n times a1 x1 of n plus a2 x2 of n. Spread n over those two. So you have a1 n x1 of n plus a2 n x2 of n. What is this? It's here. So this one here is the same as here. So this is y1. So this is equals to a1 y1 of n plus, and this one here also is this one here. So this one here. And so this is A2, Y2 of n. So the system is linear. So the system is linear. Okay, let's take the next one. For the next one, B, so we have y of n equals x squared of n. Is this linear or not? Or non-linear? Okay. Is it linear or non-linear? So, okay. We'll do the same. So, take x1 to be an input to the system. So, x1 of n applied through the system to get x1 squared of n. x2 of n applied to the system. So, we'll get x2 squared of n. And now we let x of n is a linear combination of those two inputs and apply it to the system. So y of n here is equal to x squared of n, which is equal to a1 x1 plus a2 x2, the whole thing squared. And this is equals to a1 squared x1 squared of n plus 2a1 a2 x1 x2 of n plus a2 squared x2 squared of n, and this does not equal to ay1 of n plus a2 y2 of n. So you have a nonlinear system. Okay? So we have a nonlinear system. As for part C, which is y of n equals to ax of n plus b, this is also nonlinear system. And I will let it for you. Please prove it. You prove it. Okay, I'm going to let it as an exercise for you. But it is nonlinear system. Just show it by exactly doing the same as we did in the previous two examples. Okay, enough from linearity. Let's go to another classification. The second classification is the time invariant. And sometimes we call it shift invariant because we have a discrete system. So it's time invariant or shift invariant. Okay? Both of them works. Okay, what do we mean by time invariant? If we have x of n applied at certain instant of time through t, then we get y of n. Now, if x of n is shifted by time, so we have a shift, either positive or negative, both works, then and now this shifted input is going through the system. If we get y with the same shift, then we say that, okay, the system is, if this is true, then you have time invariant system. Otherwise, you have time variant system. What do we mean by time invariant? Actually, most systems are time invariant systems because let's take a machine. If you apply electricity to a machine today, it will work directly. If you postpone applying the electricity for tomorrow, until tomorrow, and you apply the electricity tomorrow, then the machine will work tomorrow. So the output will be shifted exactly the same amount as you shift the input. Okay, so this is what we mean by shift invariant or time invariant. Okay, how to check for time, invariant or time invariance. Okay, to do this, step number one, we have to apply x of n itself. So we apply x of n through t and get y of n. So this is my step, or the first step. Step number two, given x1 of n to be shifted version of x, find y1 of n, and apply this x1 of n to the system to get y1 of n. So first apply x, get y, then take x and shift it by k and call it x1 of n. Apply x1 and to get y1 of n through the system. Now, step number three, shift y1 of n in step 1 by k. So, to get y of n minus k. So, we shift y of n here, this y of n, shifted by k, to get y of n minus k. Now, if this one is equal to this one, so you have equality, then the system is time invariant. Otherwise, you have a time variant system. So if y1 of n equals y of n minus k, then the system is time. And it's exactly implementing those two steps. Those steps, three steps here, is actually applying the definition of the time invariant. Apply x, get y. If you apply n minus k as an input, you have to get y of n minus k. So we took y of n, apply it, take this one and shift it. If both are equal, then this is what we have here. Okay, let me take an example and show you how this works. Example. Y of n, let's take a, y of n equals to x of n minus x of n minus 1, and b, y of n equals to n x of n. Okay, let's take part A. Step number 1, apply the system itself. So apply x of n and get y of n. So we have y of n equals to x of n minus x of n minus 1. So actually the first step is just stating the system itself. Y of n equals x of n minus x of n minus 1. Step number 2, we let x1 of n to be a shifted version of x. So this is equals to x of n minus k. And apply it to the system once again. So y1 of n is equal to x1 of n minus x1 of n minus 1. And substitute for x1, so this is x of n minus k minus x of n minus k minus 1. Okay? So this is y1 of n. Okay. Step number 3, take y in the first step and shift it by k. So y of n minus k is equal. So we'll take every n here and substitute it by n minus k. So this is n minus k minus x of n minus k minus 1. Is y1 of n and y of n minus k, are they the same? Are they equal? Yes, they are. So y of 1 of n is equal to y of n minus k, and we have here a time invariant system. Okay. Move to the next part, or the part B of the question. Now, for part B, first of all, we have y of n equals to nx of n. So this is step number 1. Step number 1, just state what is y in terms of x. Step number 2, we let x1 of n equals to x of n minus k, and apply x1 to the system. So you have y1 of n equals to n x1 of n, which is equal to n x of n minus k. Step number 3, shift the y of n in the first step. So you have y of n minus k equals to, so we have to replace every n here by n minus k. So this one will be n minus k times x of n minus k. Is this one and this one, or are those the same? Are they the same? No, they aren't. So y1 of n does not equal y of n minus k. So you have time variant system. Okay, so we have a time variant system. Okay. Okay, so enough from causality, the time invariance. Let's move to another classification. So 3, we have a causal system. Causal system, and sometimes we call it realizable. realizable system, a system that can be realized in real life. Okay, in a causal discrete time, system, the n-zeroth output sample y at n0 depends on only on input samples for x of n for n less than or equal n0. So we can say that y of n is transformation of x of n and previous x's. X of n minus 1, x of n minus 2, and another or other previous x's. Okay, so if y of n is a function of x of n and previous x's, then we call the system causal. If it depends on x of n and future x's, then it's a non-causal system. So the future values are non-causal and an unrealizable system. It only can be in mathematical modeling and prediction. So the future values can be in mathematical modeling and prediction or estimation of future values or prediction of future values. Okay, let's take an example. If we have y of n equals to x of n minus 1, this is A. B, y of n is equal to x of minus n. Okay, for part A, y of n is equal to, depends on the exact instant, the same instant of time, and the previous instant. So this one definitely is causal. So this one is causal system. No doubt about this. Okay, what about this one here? If you take an example, let's say y of 1, it's equal to y of minus 1. So this is causal. But if you take y of minus 1, so this one is equal to y of 1. So the instant at minus depends on future value. So this is a non-causal. And it's enough to show that it is non-causal by just demonstrating an example to diffuse that it is a causal system. So it's a non-causal system. Y of n equals x of minus n. Okay. Part 4, or property 4, or the classification number 4 is stable systems. A discrete time system is stable if and only if for every bounded input the output is also bounded. Okay, mathematically, if x of n is bounded for all n, this implies, or then y of n is less than beta y. So y of n is also bounded, where beta x and beta y are finite positive constants. And this is the upper bound of x, and this one is the upper bound of y. Okay. This type of stability is called bibostability. This type of stability is called bounded input bounded output shorthand notation bibo stability. Criterion. This is called bibo stability criterion, which means that if you guarantee that x is bounded, then y will be bounded if it is bibostable. So you have to, first of all, to make sure that x is bounded first. If you get for every bounded input that y also is bounded, then the output is stable. If you have a bounded input but the system goes unboundedly, then the system is astable or unstable. Let's see those two examples. Examples A, y of n is equal to e to the x of n, and B, y of n is equal to summation from k equals 0 up to n x of k. This system here is called an accumulator. It accumulates value. Okay. Solution. Okay, we'll start with A. So we'll have y of n equals e to the x of n. Now, to start with, I'm going to take the absolute value of both. This is how we tackle the problem of checking stability of systems or bibostability of systems. You take the absolute value of both sides of the equation of the system. So you have absolute value of y equals absolute value of e to the x of n. Now, I'm gonna move the absolute value to the x in the power of e. So this one definitely will be e to the absolute value of x of n. Why is that? Now, e to the x is a number, depends on whether the value is positive, x of n is positive or negative. If it's negative, then you have a number, a very small number. It's 1 over e. So this is small number, less than 1. If x of n is positive value, then this one will grow up. So if it has a power, positive power or negative power, it depends on the value of x. This one will have a value. Now, if you take the absolute value, then you make sure that this x is always positive. So this one will be definitely greater than this one. Now, I'm going to take also the upper limit of this. So I'm going to say, okay, this is also less than or equal e to the beta x. Why? If you take the upper value of this one. This one is always greater than this one, so this one, e to the beta x, is always greater than e to the absolute value of x of n. Now, this one is constant. Exponential, the exponent of, or the e to the power beta x is a constant value. I'm going to call it beta y. So my beta y is definitely greater than so if we guarantee that this one is okay, then this one is also okay. So the system is bibostable. So you have a bibostable system. Okay? Now, let's move to the next part. And see how can we prove it. Part B, we also have y of n is equal to summation from k equals 0 to n x of k. So we are adding values. We'll take the absolute for both. Now, this one is our y, our target, to prove it as here. I'm going to take the absolute value and move it inside. So I'm going to say it's not equal, actually. If you take the absolute inside, then this definitely will be greater than the sum. The sum of absolutes is definitely greater than the absolute of the sums from k equals 0 to n. Yeah? This is true because if x of k has positive values and negative values, then their summation could be positive or negative, but some of them will subtract from each other. If you take the absolute value, then all values are positive, they will add positively. So their summation definitely will be greater than this. The equality holds if all x's are positive or all x's are negative. So the equality will hold. Okay, now I'm gonna go to make sure that this x has an upper limit. I'm gonna take the upper limit to substitute all values of x. So this one will be less than or equal summation of beta x from k equals 0 up to n. So I'm going to replace all the values of x of n by its upper limit. So you have also an inequality. And this one definitely greater than this sum, definitely greater than this one equals to this one. So we have y of n less than or equal summation beta x from k equals 0 up to n. Notice that this n here is the same index as here. So as you grow in time, this one is also will grow. What will be this summation? This summation will be n plus 1 times beta x. So absolute value of y of n is less than n plus 1 times beta x. As you grow in time, this upper bound will grow in time, and this one is not equal to beta y. It's not equal to a constant. So the system is, a stable system. Or non-stable. So it's stable system or non-stable system. Okay? Okay. Property or classification number 5, we'll talk about static and dynamic systems. Okay? Sometimes statics we call it memoryless memoryless system. And dynamic, we call it system with memory. With memory. So if you have a system that depends on the actual instant of time or the present instant of time, then we call it static system. This one is static. Notice that y of n depends on x of n with the same instant. So you have a static system. N, you have n, but you have n minus 1, so you have to have a memory. If you have a memory, then this is a dynamic system. So you have a dynamic system or system with memory. And notice that not only minus, but plus. I mean, if you have a system, let's say y of n equals to x of n plus 1/2 x of n plus 1, this is also dynamic. Because y of n depends on different instants of time. Okay, so you need a system with a memory. Okay, the last one, or the last classification, is the passive and lossless systems. Passive and lossless. So the system, if it's not passive, then it's active. What is a passive system? The passive system that the output energy, if you apply an energy signal to a system, signal. And you get such that summation of y of n magnitude squared from n equals minus infinity to infinity is less than or equal ex, which is the summation of x of n magnitude squared from n equals minus infinity to infinity, less than infinity, then we call the system passive system. So the system is passive, which means that your output will never exceed the amount of energy of the input. So if it is exactly the same, we call it lossless. If it is less, then it's a passive system. If it's greater than, y is greater than this, then we call it an active system. Okay, so let's take a final example. If we have y of n is equal to alpha x of n minus n0, capital N, where capital N is positive integer, then summation of y of n magnitude squared from n equals minus infinity to infinity equals to summation of alpha x of n minus capital N magnitude squared from n equals minus infinity to infinity. We can distribute the absolute squared and say that this constant alpha magnitude squared summation x of n minus capital N squared from infinity to infinity. Okay? Now, this is y of n, this is x of n, this is actually our Ex. So the system y of n depends on the magnitude of alpha. If the magnitude of alpha is less than or equal 1, then we have passive system. If the magnitude of alpha is equal to 1, then we have a lossless system. And if the magnitude of alpha is greater than 1, then you have an active system. Okay, so don't worry about the shift, x of n minus n0, since you are summing the values from minus infinity to infinity, summing x of n or summing x of n minus capital N is the same. It's always the energy of x. So the energy of y will be exactly the same as the energy of x is if the magnitude of alpha squared is equal to 1. So you have a lossless system. If the magnitude of alpha is less than 1, then its square is also less than 1, so you have a passive system. If the magnitude of alpha is greater than 1, then its square is also greater than 1, and we call it an active system. Okay, with this we end up with the classifications of systems, and we'll see you in next lecture. Thank you very much for being with me.